Empower your students to be more authentic, impactful writers with Grammarly's comprehensive AI writing assistance. Use it to help students
I'm saving big with TD Insurance for being a claims-free hybrid driving university grad.
Wow, Dave. You should have your own jingle.
Who saves with TD Insurance because he's a claims-free hybrid driving university grad who signed up online. It's Dave. You can totally save, just not exactly like Dave.
With over 30 ways to save, real value starts with TD Insurance. TD. Ready for you.
One of the great challenges in this world is knowing enough about a subject to think you're right, but not enough about the subject to know you're wrong. There's like a gazillion hours of me on the internet. In almost every case, I'm talking about the universe, black holes, the Big Bang, time travel, God. But what I'm gonna do in this masterclass is teach you how to think. The goal here is to train your mind how to see the world differently, how to question what others say. I've come to realize that there are three categories of truth: personal truth, political truths, and the objective truths that shape our understanding of the universe. The interesting thing about an objective truth is that it's true no matter what. Imagine that. By the time we're done, you will be equipped with some of the methods and tools so you can turn data into information, information into knowledge, knowledge into wisdom. We all have susceptibility to bias. Search engines on the internet are the epitome of confirmation bias. And you're gonna use that as evidence that you are correct? No. The good thing about science is that it's true whether or not you believe in it. What does it mean to be skeptical? What does it mean to be convinced by data? A proper skeptic questions what they're unsure of, but recognizes when valid evidence is presented to change their mind. I will equip you to not only find objective truths, but then communicate to others how to get there. It's not good enough to be right. You also have to be effective. The less connected you are to what is objectively true, the less likely you will be able to make decisions that will benefit your life, the life of your family, and even civilization itself. I'm Neil deGrasse Tyson, and this is my masterclass.
vanilla flavored shreddies. Same great square, new delicious flavor.
Okay, if there's one AI site builder you need to meet, it's this dope tech from Wix. Now, this whole flow is a conversation, so your words actually build your website. I'm going for a store, and after a free-flowing conversation, I get this detailed site brief. And just like that, my first draft is ready. Now, that's dope. Next, you can really get in there and style it your way. Here's the fun part. You can regenerate this whole thing over and over, or you can tweak something specific, like your layout. Let me describe what I had in mind. Yeah, that's fire. If there was ever a time to speak life into your dreams, it's right now using the Wix AI website builder.
From idea to submission, empower students to do their best work with Grammarly's comprehensive AI writing assistance. What if they could jumpstart ideas for any assignment? What if they could be more transparent?
Getting that yes to credit allows me to do things in life that I wanted to do. I've been able to rebuild my credit, take my family and friends for dinner without having to worry about it. That yes to credit was just the beginning for me.
Your firsts in a new country are unforgettable. First time feeling the snow. First night in your new home. With Scotiabank's Start Right program, I had support every step of the way. No account fees for the first year, free international transfers, credit to help you start strong. It's about building a life you love. Start your journey right with Scotiabank Start Right.
Empower your students to be more authentic, impactful writers with Grammarly's comprehensive AI writing assistant.
When your business is growing out of control, it can be disorienting. But with SAP, AI agents use all the right data to help you get out of the woods before you even know you're in them.
Secret. It has powerful ingredients that fight odor-causing bacteria for all-day protection.
saving big with TD Insurance for being a claims-free hybrid driving university grad.
Wow, Dave. You should have your own jingle.
Who saves with TD Insurance because he's a claims-free hybrid driving university grad who signed up online. It's Dave. You can totally save, just not exactly like Dave.
With over 30 ways to save, real value starts with TD Insurance. TD. Ready for you.
Empower your students to be more authentic, impactful writers with Grammarly's comprehensive AI writing assistance. Use it to help students brainstorm better ideas before they write. Document their writing process. Check for plagiarism and AI-generated text. Cite sources correctly. Get real-time feedback. And much more. Hear it from the former CIO of Wharton Business School. It's not just a grammar tool. It's your responsible AI writing assistant for the new era of communication. Download Grammarly for free today.
My freshness? Proof that my secret aluminum-free deodorant showed up, even when my alarm didn't. It has powerful ingredients that fight odor-causing bacteria for all-day protection. Smell check? I'm good. Secret.
Old Spice, super hydration. Keeps me 24/7 moisturized and smells like a Fiji vacation.
Who are you talking to?
Oh, sorry, gotta go. It's your mom. She just wanted my advice.
Why doesn't anyone ask me for skincare advice? Look, this is vitamin B3, skin conditioners.
Old Spice has all that stuff.
Ooh, can I try some?
Oops, looks like we're out of Old Spice.
New Oreo Cakesters. The Oreo taste you love. Now in a deliciously soft cake.
Okay, welcome back. So I'm going to basically fast forward through this. It's going to be more of the same, just me placing down these actors to light the level. Great reveal, and I'm noticing this is not quite aligned as I wanted it to be, so I'm going to move it a bit more centrally like so. Then we go into the corridor and we're keeping it nice and dark and moody in here. We've got I had to put a light here so that it would illuminate this, what's going on, and to see the railings that shut, etc. So that's it, that is my lighting. Hello and welcome. In this lecture we're going to be setting up a game mode and a custom player pawn so that we can walk around our level as a first-person player ready to play some gameplay mechanics. Let's dive in and see how this works. So we've already seen how when I hit play, I just go straight through the floor here. So we kind of want to fix that so that we can play inside our level without fear of falling through floors. So the problem is that this SM floor mesh does not have any collision set up on it. So we can hit the browse to SM floor and content browser button. We can open up the SM mesh editor and dock it to the main window. And then we can go to the show button and hit show simple collision and see that there are no simple collision meshes. To add one in, we're going to go to the collision button in the toolbar and go to add box simplified collision, which automatically adds it around the mesh. Now, just to make sure we don't fall through this floor, I want to make that box a little bit thicker. At the moment, it's kind of 0 thickness. So what we can do is go in the details pane, scroll on down, where we're going to find the primitives collision section, and then under it there is primitives. And this shows us the different primitives that make up the collisions. And some of the primitives are things like spheres, boxes, capsules, etc. We've got boxes. So let's open up the box. We can see its center is here. We can see the rotation. We can see the extent, which basically means how large it is, and the Z extent is 0. So let's make that 10 centimeters instead. So you can see that's made the box slightly thicker. But I don't want our character to be standing on top of the floor, so what I'm going to do is I'm going to change its center to be at -10. So that, basically we've got that box, but it's underneath our floor. So we can go ahead and hit save to the mesh, and now if we hit play, hopefully, there you go, we are able to walk around on the floor without falling through it. Now there may be other meshes that you discover that have similar problems and that you can't you can pass through. In this case, the doors for me are not actually wide enough to fit my character, so I'm going to have to open these doors a smidge more. Okay, so now that those doors are wider, we should be able to fit through them no problem, and we do. And we can now walk around our level as a first-person character. However, this first-person character is set up for a first-person shooter with first-person shooter arms, and that's not what I want. So we're going to adapt this character for our own uses. So let's find where that first-person character is, and that's under the content first-person blueprints, and we've got first-person character in here. I'm going to right-click on it and create a child blueprint class, which I'm going to call BP_player. And this player, we're going to move to the root of content. Click move there. And then what we want to do is create a new default game mode and set this player as the default to get spawned. But before I challenge you to do that, let's modify this player so that we remove the arms that are there. So when we open up the BP player blueprint, you can see that we've got a bunch of components here. One of them is the mesh 1P, basically mesh first person, which is the arms. And what we can do here is we can simply go down to where we've got the skeletal mesh property and clear that so that we don't have any mesh selected to render for the first person. Now, if we were to play as the first-person player, we'll see that we now works exactly the same, except we've got no mesh arms. But that requires a game mode. So let me refresh your memory on how we create a game mode. We go over into a level, we go to the blueprint button in the toolbar, we go to where it says game mode, and we've currently got a Crypt Raider game mode. And what we want to do is go into this and click create, and we want to create a new game mode based off of this Crypt Raider game mode. The Crypt Raider game mode is a C++ game mode, so what we can do is we can create a blueprint version of it to link to other blueprint classes. So let's click on the Crypt Raider game mode, click the root of content, and we're going to call this game mode the BP_Crypt Raider game mode, and hit save, and then we have our game mode launch up like so. So I'd like to challenge you to set up your own game mode. You're going to set it as the project default so that it's being used in any of the levels you set up in this project. Set the default pawn for the game mode to that player pawn that we've just created and removed the arms from. And check that that is the pawn that spawns in your game now. Pause the video and have a go. Okay, welcome back. So, first thing, because I'm here in the game mode already, I can select the default pawn class. It's currently set to the first person class, but I want to change it to the BP player instead. I'm going to save that, and then I'm going to go over to the dungeon level, go to the blueprint button, and I'm going to check that our project default, in fact it looks like we've already done this, the project settings, basically by having created it here, is using the BP Crypt Raider game mode already. So if I go ahead and hit play, you can see the pawn created moves like a first person pawn, but I no longer have those arms in front of me, which is more in keeping with the style of genre that we've got here. Great stuff. So we've set up our character blueprint ready for some gameplay action, which we will start to do in the following lectures. I'll see you there. So in the previous sections, we made heavy use of inheritance through our actors. Now, what is inheritance? Inheritance is when a child class automatically has all of the functionality of its parent. We say essentially that the child is a parent. So where did we use that previously? Well, for example, in our moving platforms, we had an actor that was a moving platform actor. And then we had different children of that actor that gave us the spinning, rotating platforms, the up and down platforms, the side-to-side pushers. Those were all children. They all were movers. You could say the moving pusher is a mover. We could say that the rotating baton is a mover. So there is an alternative to using inheritance, which is a bit all or nothing, and this is composition, which is a bit more pick and choose. You get to say that Class A has an instance of Class B. It can choose to use its functionality, but it doesn't have to. It's not tied into being Class B. It can just choose to take the bits it wants. So we say that Class A has a Class B. So let's have a look at some examples of inheritance versus composition using something quite natural, I think, talking about inheritance in the animal kingdom. We might have at some examples too. It's not tied into being. Class B, it is composition using actor, and it has a method on it, which is to live. It lives when you call that method. Now, it makes sense to have things like a mammal that inherits from this because it also needs to live, so it needs all of that functionality that the animal has, but it adds some more functionality, such as making milk. We might also have a reptile that has the functionality, the added functionality of laying eggs. Now, it's fair to say that a mammal is an animal and a reptile is an animal as well. Now, we could go onwards and say, okay, we've got a cow. Well, a cow clearly is a mammal. It needs to make milk, and by extension, it also needs to live because it's also an animal. A snake is a reptile and it is an animal, but it is not a mammal, so that makes sense too. But what about a platypus? A platypus suddenly needs to both be a mammal and a reptile because it needs the functionality of laying eggs, and it needs the functionality of making milk, and it needs to be an animal. So it gets a little bit confusing here with inheritance, and inheritance can put us in a straitjacket and make these situations really hard to resolve. Which is why composition is what comes to the rescue here. It's the has a relationship. So instead of trying to build this taxonomy of classes with animals and mammals, etc., what we do instead is we say we've got a milk-making component, and that component has the functionality of making milk. So the cow would have one of these milk-making components, and it gets its functionality from there. The snake can have its egg-laying component, and it gets its egg-laying functionality from there. And the platypus can have both components. It doesn't have to pick and choose one component, it can have all of them, and it gets to share the functionality. just fine. So let's take the example that we're going to be using here, where we've got for a mover. We've got something that wants to move. We might have started setting it up as an inheritance and is a relationship. So we've got a mover that inherits from the static mesh actor, kind of like we've done in previous sections. And then from the mover, we might inherit a moving door or a moving wall. But what happens if we wanted to do a moving light? How could that be done? We can't inherit from mover because that would make it a static mesh actor, and we want to use a light actor instead as the parent for moving light. How could we resolve this problem using has a relationships instead? Pause the video, have a think about it, get out a piece of paper and jot down some of your thoughts. Okay, welcome back. So this is the way I would resolve the problem. So we could have our moving door and moving wall both inherit from static mesh actor. That's fine. And the moving light can inherit from the light actor. But now the difference is that we include this has a relationship in here as well. So the moving door, the moving wall, and the moving light all can have a mover component on the actor. And this is where actor components come in really handy. And we're going to put this into practice in the next lecture. So I'll see you there. Hello and welcome. In this lecture we are going to be adding a new component in C++ that we can add to our actors to add in some functionality using some composition essentially. Let's dive in and see how this is done. So I want to add a section of wall that disappears from view when we place an object on it. So what I'm going to do here is I'm going to go to the content drawer and I'm going to search for the dungeon wall in here, and I think I want this one with a nice cut out section where I can stick the statuette. So I'm going to drag this into the scene and I'm going to rotate it by 180 degrees and try and position it accurately. There we go, brought it down to the floor level and it's looking okay. Now what I want to do with this actor is I want to be able to add a component onto it that gives it the capability of moving itself. Now we've dealt with components before, we've added ones already created by Unreal, but we've never made our own in C++, so that's what we're going to do in this lecture. So what we're going to do is go to this add button and you can see there is an option within here to create a new C++ component. Now within here there are a couple of options for different types of components that we can inherit from, so the different types of components we can build. There is an actor component which there is an option within here to create a new C++ component. Now within here there are a couple of options for different types of components that we can inherit from, so the different types of components we can build. There is an actor component, which is a component that just sits on an actor, any actor. And then there's a scene component, which is an actor component that also adds in a transform and the ability to attach to other scene components. We don't need this functionality, so we're just going to go for the actor component for now. We will be using scene components later on in the section though. So let's go ahead and hit next. Now we've got to name our component, and we're going to call it simply the mover. And we'll go ahead and hit create class. And instantly it opens up in Visual Studio for me and Visual Studio Code. And I can see that there is a mover.h and a mover CPP, just like we had with our actors. Interesting to note that the prefix to this class is u. Previously with the actor, the prefix had been a. And the other thing to note is the name of the tick function is different. With a component, its function is called tick component instead. But otherwise, it is the same. And if we go over to the C++ class, you can see that there is a tick component function in here. So I'd like to challenge you to log a message on tick. So you're going to add a new log message, add a component to an actor, add your new component to some actor, and see if it prints the message that you have written. Pause the video. video and have a go. Okay, welcome back. So let's give this a stab. So in the tick component, we're going to type ulog to get the ulog macro to come up. We're leaving it as a display setting, and in here I'm going to type in mover is ticking! Exclamation points, of course. Let's go back into Unreal, and actually what you can do is do a Control Alt F11 from any place. Actually, you can do it in Visual Studio Code, and it brings up the live coding window automatically. When it's completed, it brings you back over to the editor, just saves you an Alt tab. So what we can do now is you can see this actor does not have our new component on it. So let's go to the add button, and we're going to search for mover, and there you can see there is a custom component called mover. If I go ahead and add it, you can see it adds it to a separate section to the static mesh components and the other components up the top. That's because these components here, the ones that are attached to each other, are all the scene components, the ones that have transforms that can be attached, whereas the normal actor components, the more simple actor components, go in a separate section down at the bottom, and they just go in a list. They don't get attached to each other. So we've got the mover down here, and at the moment it doesn't do very much. Let's bring up our output log and dock it to the layout, and let's go ahead and hit play in the game, and you can see that we are indeed getting mover is ticking displayed in our output log. Great stuff. We've created our Hello and welcome. In this lecture we're going to be learning how we can get a pointer to the owning actor of a component. We're going to find out what a pointer is, what addresses are in memory, and we're going to print them out into our log messages as well. Let's dive in. So let's take a second to understand a core concept of what's going on in programming in general about variable addresses. What is an address of a variable? Well, we store all of our variables in memory, in this RAM chips on your computer. And variables require memory to store their data, so a floating point number requires either 32 bits of data or 64 if it's a double. An integer requires a certain amount of memory. Also, the bigger the structs you have, or the bigger the classes you have, like actors can be very large and encompass a lot of data, might require even a few kilobytes of memory per actor, things like that. Well, that memory has to live somewhere on this large field of empty data that is your memory banks. And that location is known as an address. So how does this work in practice? Well, imagine we have this large field of zeros and ones that is the data on your RAM. Well, then the variable, an A-actor variable called myActor, needs to have a certain location within that memory that is allocated to, is essentially, in fact, we don't actually count the individual ones and zeros, we count in steps of 8, but that's not too important. We count the bytes. Why? So we know that the actor would require so many bytes of data, and so that tells us where to find the data about this. So we've got a chunk of memory that is allocated to the myActor variable. We've got another chunk of memory that's allocated to an empty data is we make up your actor. So this can be a fairly costly procedure because your CPU has to go through and evaluate each piece of memory in the original and put it into the new location, which takes up time. Now there's a way around this using something called a pointer. So here, instead of storing the entirety of the myActor, we have a variable called a myActor, or an actor, A-actor pointer, that doesn't store the whole actor, it just stores the address where you can find an actor. So you can see it actually uses up a lot less memory to store an address, and then what we do is into your actor we store the address of my actor. So it ends up pointing to the original actor rather than copying the data over, hence the name pointer. Now this isn't the actual syntax in C++. In C++, the syntax is much more condensed. We say that something is a pointer by putting a star after the type. So A-actor star means that this is an A-actor pointer. And to get the address of a variable, we use an ampersand. We won't be making much use of this address of just yet because there's a lot of functions in Unreal that return pointers. So we just need to know how to use those pointers rather than create them for the time being. So one such function that allows us to get access to other objects in our scene is getOwner. So where does this apply? When we've got a component, it is owned by an actor. So if we wanted this component to talk to our actor, to get its location, to set its location and do things like that, then we need to be able to get a pointer to that actor. We don't want to take a copy of it. In fact, we don't want to take a copy of it because we want to be changing the actor. If we were making a change to a copy, it wouldn't actually show up in the scene. So we need to be able to store a variable that is a pointer to an actor. The way we do this, as we've just seen in the slides, is to have an A-actor type, but then we put a star at the end, which tells us this isn't an A-actor being stored here. This is just the address of an A-actor being stored. So we take the A-actor and we're going to call this owner, and then we're going to set that equal to the result of calling getOwner. So that getOwner is a function of an actor component, which allows you to get an owner pointer, get an actor pointer that points at the owner. Put a semicolon at the end of that line, and what we've got here is a variable that stores the address of an actor that owns this particular component. So I'd like to challenge you to do something by printing the address of this variable. So use the aActor variable and use the %u format specifier in the logs, the getOwner. So the getOwner is a function of an actor component which allows you to get an owner pointer, get an actor pointer that points at the owner. Put a semicolon at the end of that line, and what we've got here is a variable that stores the address of an actor that owns this particular component. So I'd like to challenge you to do something by printing the address of this variable. So use the aActor variable and use the %u format specifier in the logs. So %u essentially means that you're using an unsigned integer. That means an integer that can't be negative, which makes sense because addresses can't be negative when we're talking about where to find memory. And then figure out, what does it print? Go and play, see the log message, see what it prints out. Does it change between different plays if you stop playing and start playing again? And what about if the mover is on multiple actors? Is there multiple different addresses printed out in the console? Pause the video and have a little investigation. Okay, welcome back. So we're going to go over to this UE log, and we're going to say mover owner address :%u. So that's where it's going to put the pointer's value. And then we're going to put the actual pointer. So we're going to have the owner in here. So it's going to print out the address of the owner. Let's go over into Unreal, hit Control-Alt-F11, and when that finishes compiling, let's hit play. And what we're seeing is that the log message mover owner address is coming through, and it's giving us a very large number actually for this address. What if I stop playing and play again? Just for a second, you can see the address is quite substantially different. And that's because every time that we hit play, Unreal is creating a whole new set of actors in the scene, basically ready to play, starting from scratch. So that's why we're seeing new address locations each time we hit play. What happens if I went to this pillar, for example, and added a mover component to the pillar as well, and we hit play and scroll down to the bottom of my logs? You can see that there are each tick 2 different addresses being printed out here, because there are 2 different actors which are stored in 2 different locations in memory. So these are the 2 addresses, and you can see there's actually quite a few megabytes of difference between these 2 addresses, which just goes to tell you how much information is being stored in memory by Unreal, and also why it's important to be efficient with not making too many copies. That's it for this lecture. I will see you in the next one, where we'll be doing more fun things with pointers. Hello and welcome. In this lecture, we're going to be learning about how we can access what is on the other side of a pointer so that our mover component can get properties from the actor that it lives on, such as getting the name of the actor or getting its location. Let's dive in and see how we can do this. So it's all very well to be able to get a pointer or get an address of an actor, but we do need to be able to actually do stuff with the actor itself. And the process for doing this is a little bit tricky to understand if we're just looking at the actor. So we're going to have a look at doing some pointers to floats just here within tick component. So let's start off by creating a float, which we're going to call myFloat, and set this to a value of 5. Then we're going to create a float pointer, which I'm going to call yourFloat, and we're going to set that to be the address of the myFloat. So these are both pointing to the same address in memory. The difference is that yourFloat is an address, so I can't just print out the value. So if I wanted to do a ulog and I wanted to say yourFloat value is equal to %f, then I put in yourFloat. This isn't going to work because yourFloat is a pointer, not an actual float. So what we need to do is essentially get the value at that location. So the way we can do this, if I were to store it in a new float variable called float value, then I use the dereferencing operator, which is actually a star as well, and we put this before the thing that we want to dereference, so we then give it a pointer to dereference, which in this case is yourFloat. Now, it's a little bit strange that we use these stars in 2 different contexts. So one, we are using the star after the type.
set up the JetBrains Writer IDE for Unreal Engine. First, we will need to install Writer. You can download the installer prompts and if you already have the full Visual Studio IDE or the build tools installed, you can skip this step with your MS Build tools. For Writer specifically, we need the .NET SDK, which should include the latest .NET runtimes. Note for 3.1, but I'm going to use the third-person template. Writer. To fix this, open your project in Unreal Engine, go to Edit, Editor Preferences, and from here, General, Source. If your project and open it with Writer paths. If you purchased a commercial license, then select Activate License. Otherwise, if your usage of Writer falls under JetBrains' definition of non-commercial use, then select the free non-commercial use option. If your use case is commercial and you don't have a paid subscription, you could have tried out the free 30-day trial. Doesn't require a login. The other two options, however, do require logging into a JetBrains account, so if you don't have one, go ahead and create one. Once you've logged in on the JetBrains website, go back to Writer, and if this is a newly created account, then activate your license for non-commercial or commercial use. Lastly, just go through these last few prompts with regards to settings in Writer on your own. For low-spec PCs that have less than 32 gigabytes of RAM, I suggest turning off indexing of engine files by going to File on the top left corner, Settings, Languages and Frameworks, C++, Unreal Engine, and unchecking Index Unreal Engine source files. Otherwise, keep this setting on. Another way to improve performance in the Writer IDE on Windows is to exclude project and Writer-related directories from Microsoft Defender antivirus scans. You can do this by going to Windows Security, Virus and Threat Detection, Manage Settings, and scrolling to the bottom where it said Exclusions. Writer suggests excluding 3 locations, where your NuGet packages are installed, the Writer cache folder, and your Unreal project folder. Going back to the Writer IDE settings, let's install the WriterLink Unreal Editor plugin, which is under Languages and Frameworks, Unreal Engine, and select Install WriterLink in Engine. Give it a few seconds and click Save. Then let's enable the plugin by going back to the Unreal Editor by going to Edit, Plugins, and look up WriterLink. This plugin is
Hello and welcome. In this lecture, we're going to be learning about how we can access what is on the other side of a pointer so that our mover component can get properties from the actor that it lives on, such as getting the name of the actor or getting its location. Let's dive in and see how we can do this. So it's all very well to be able to get a pointer or get an address of an actor, but we do need to be able to actually do stuff with the actor itself. And the process for doing this is a little bit tricky to understand if we're just looking at the actor. So we're going to have a look at doing some pointers to floats just here within tick component. So let's start off by creating a float, which we're going to call my float, and set this to a value of 5. Then we're going to create a float pointer, which I'm going to call your float, and we're going to set that to be the address of the my float. So these are both pointing to the same address in memory. The difference is that your float is an address, so I can't just print out the value. So if I wanted to do a ulog and I wanted to say your float value is equal to %f, then I put in your float. This isn't going to work because your float is a pointer, not an actual float. So what we need to do is essentially get the value at that location. So the way we can do this, if I were to store it in a new float variable called float value, then I use the dereferencing operator, which is actually a star as well. And we put this before the thing that we want to dereference, so we then give it a pointer to dereference, which in this case is your float. Now, it's a little bit strange that we use these stars in two different contexts. So one, we're using the star after the type, which tells us that it's a float pointer. And when you're using it with a type, it means that it's a pointer. When you use a star before a pointer expression, what you're doing there is you're saying, get me the value at this location. So then that gets the value and copies it into float value, and now float value we can just print out like so. So with all those contortions, let's go ahead and compile it and see it in action. Let's hit play, and sure enough, it's saying your float value is 5, which is the value we had originally. Now, usually we don't store the intermediate value in a variable because that's wasteful. It's creating a copy that we don't need. So what we can do instead is just use that directly in the expression where we need it. So your float value would be star your float, like so. And that's going to work in exactly the same way, except this time it doesn't make a copy into a needless variable. Now, suppose we wanted to get the name of the owner actor here? Well, the way we would do this, let's remove this stuff that we were doing with the floats, is we would dereference that owner pointer. So we do star owner, which actually gets us to the actor itself. Then we can put a pair of brackets around the owner, and then we can do a dot. So we've got the actor out of this expression, and we can use a dot to get something in from inside the actor. So we can do get actor name or label, which is going to return us a f string. So we can do f string name equals to this, and then we can print out mover owner %. content S, and then instead of using owner here, we're going to do star name, remembering that we need to put the star in front of a name. That's yet another use for that star operator. We've already encountered 3 of them. One is with this string. That's the first time we've seen it. Then it's here with the type, and it's also here for dereferencing. Lots and lots of uses for exactly the same character, but that's how it is with C++. Let's go and try it out and hit play. And now you can see that it's printing out the name of the actors that the mover is attached to. So we've reached through that pointer with the dereferencing operator and been able to call a function on a different object. Now there's actually a much more compact syntax for doing this, because it's so common for us to want to get a function or property from a pointer object. Instead of having to do this with the parentheses and the dereferencing operator, we can merge this all into one. We can remove all of this, remove the dot, and instead we use this arrow operator. So we do owner arrow get actor name or label, and this does exactly the same thing, except it's a lot easier to write. So generally speaking, we'll end up with the rule where if we have got a pointer, we use the arrow operator. If we are using a struct like an f string or an f vector, we use the dot operator. So I'd like you to print the actor's location using this new knowledge of how we can use pointers. So I'd like you to call getActorLocation. You're going to be using the arrow operator to look through the pointer and call that function on the object at the other end. You're going to store the f vector that results from that. Then you're going to call toCompactString, store the result in a new f-string variable, and print that to the log. Pause the video and have a go. A new FO get equal to the owner. I'm going to say that the mover owner is this with location percent like so, and then hit Control Alt F11, and we'll go ahead of having a Hello and welcome. In this lecture we're going to be understanding the main steps involved in compiling C++ files in Unreal. Let's dive in and see how they work. So it's soon going to be time for us to start using code from the outside, from other files, and we need to learn how this works in C++. To do that, we need to take a little bit of a detour and understand in more detail what's going on when we compile our C++ code into binary. So here are the compilation steps that are used. We start off with your code, your C++ files, your header files, all in various text files. These get fed into a tool called the Unreal Header tool. Now, this tool is responsible for taking all the Unreal specific pieces of syntax and using them to generate more C++ code. So let's have a look at some examples of where we've got this Unreal specific syntax. This U class in capital letters, that is Unreal specific syntax, and so is the Crypt API thing here and the generated body there. And basically what's going on here is the Unreal Header tool will see these different pieces of syntax in your code and go, okay, I need to do my job, I need to go in there, I need to add a bunch of stuff. It's going to replace your generated body with a bunch of code that makes our lives easier when using Unreal. It also does things like the U properties and U functions. It adds all the stuff that it needs so that it can communicate with the blueprint world. So that is the first step. It converts all of its Unreal specific stuff into actual C++. Once we've got the actual C++, we can then feed it into a standard C++ compilation process, which takes 3 steps. The first is to deal with the pre-processing step, so this doesn't actually touch any of the C++ syntax, and actually only deals with lines that start with a hash. So we've got a few of these pre-processing directives. These are dealt with by the preprocessor. The next step is what we actually call the compiler. It takes our code and it converts it into executable binary, but it doesn't quite complete the step because it only does it on individual C++, what are known as translation units, basically C++ files. So it takes a C++ file and it translates that into binary individually, each individual C++ file. And then the third step is the linker, which brings all of that together and outputs an executable that we can actually run, a single executable. So let's have a look at these standard compilation steps in a little bit more detail with an example file. So imagine that we had a game.cpp, and it's a very, very simple game because all it does is add 1 and 1 together. But to add 1 and 1 together, it is having to use a function that's declared in a different file, in the math.h. So the math.h declares add, but it doesn't actually define what it does. So that is done over in the math.cpp, and you can see it's a very simple implementation indeed. Now, what happens at the preprocessor step? Well, like I said, it deals with any preprocessor directives. Which are things that begin with a hash. So the hash include math.h basically means just copy everything in math.h into here. So what it does is it takes these two files and it combines them together to create a new output file called game.i, basically game.include, and you can see that it has included the definition from math.h and has replaced the hash preprocessor directive. So now game.i has got a definition for the add operation. And then we run the preprocessor on math.cpp, but because it doesn't have any preprocessor directives, basically nothing is changed there. The next step is the compilation. It's probably the most important and complicated step because what it does is it takes that C++ in each individual .i file and converts it into binary. But it's not complete binary because, for example, my game doesn't actually know how to implement add. It just knows the shape of that add function. So that needs to be filled in later, and that's filled in by the linker. So the linker is going to take the binary created for the game.obj file and the binary created for the math.obj file and bring them together to make a game.exe, which combines the binary for both and finally is a complete executable that we can actually run because it's got the definition for everything it needs. Now, why do we have such a complicated process? The idea here is that it speeds up our compilation time, because if I only made a change to game.cpp, I don't actually need to run the entire compilation process. All I have to do is run the bits involving game.cpp. So I'd run the preprocessor only on the CPP, then I'd run the compiler only on the game.i, and then I can reuse the math.obj file from before. I don't need to recompile it because nothing has changed in that. Similarly, if I only changed math.cpp, I wouldn't have to recompile the game.obj file, which is why this is a more efficient process and why we're doing it in the first place. So I'd like us to do a little experiment and try and figure out, why do we include mover.h in our mover.cpp file? What's the reason for it? Why can't we just compile the C++ file without including mover.h? So the experiment we're going to do is we're going to comment out the hash include line, so using a double / to make a comment in front of that line, which will basically make it get stripped out by the preprocessor instead of the preprocessor replacing it with the contents of the file. We're then going to recompile, and I'd like you to have a look at the error messages that come out and see what it says, to see if you can try and understand what it is that we're including this mover.h for. Pause the video and have a go. Okay, welcome back. So let's put a double / at the beginning of this line, which basically makes it null and void. And then we're going to do a Control-Alt F11, and we're going to have a look at the output of live coding. So look, we've got some errors straight away, very, very early on. And what it's saying is that uMover is not super at uMover here what this is. So that's why we are hash including the mover.h, because mover, and it derives from uActor component, and it's got these methods, etc. It's declaring what it means to be that class. So without that declaration, the C++ compiler can't continue, and that's why we need to include that header file. Great stuff. So hopefully you now understand a Hello and welcome. In this lecture we're going to make our mover do some moving by checking a checkbox. We will enable it to move and move at a constant speed, and we're going to be doing this using some library functions this time from within Unreal. So it'll put all of our knowledge of header files and includes to the test. Let's dive in and see how it works. So the way I want this mover to work is that I want it to move smoothly from where it started to a target offset over a period of a certain number of seconds. So the way we're going to need to configure this is to add in some U properties into the header file. So let's start off by adding a private section to the header file, and then we're going to add a U property that's going to be edit anywhere, which is going to define the offset, the move offset. So how far this mover should move when activated. So the way we're going to do that is we're going to use an F vector, and we're going to call it the move offset. Like so. I won't give it a default value. We'll do that in the editor. Then I'm going to create another U property, which is again going to be edit anywhere, which is going to be the amount of time it takes to move to the target. So we're going to have that be a float, which is move time. I'm going to set that at a default value of, say, 4 seconds. Now there's one more thing that I want to put in here, which is a boolean, just for now, which is going to allow us to activate the mover so that it's going to move down when we activate this boolean. So let's create another U property, again edit anywhere, so that we can edit it even while we're playing. And this is going to be a boolean saying should move, and by default it's going to be set to false. So when we check this off in the editor when we're playing, it's going to go and move to its target move offset. Now previously when we had a moving component, we did all the steps manually, but I want to show you that there's actually some functionality built in to do a lot of the calculations we need. It's built right into Unreal, and there's a function called vinterpconstant2, and what's interesting about it? Let's have a look at the remarks. So it interpolates a vector from a current vector to a target vector using a constant step. So that means that over time, we're going to move from current to target at a certain speed, and it's going to do that constantly, which sounds like exactly what we want. We want to move from our current location to a target offset location at a constant speed. Now, you can see, if you have a look at the syntax for this function, you can see that it has a return type of f vector, so that's the new location that it's interpolating. Then it has two inputs. We've got a current f vector, and don't worry about the other symbols around this f vector for now. The important thing is that it is a current f vector, and then the target that we want it to eventually reach. Then it has the delta time, so it uses this to make the movement frame rate independent, and the interpolation speed, so how fast should we be moving from our current location to the target. Now you will notice that up here in the documentation, it actually has a section that says include, and this tells you the include line you're going to need in your C++ file in order to be able to use this function. And as we've seen in the previous video, the include line allows us to copy in the definitions from this particular file, and one of the definitions is the definition for this function. So it allows us to use this vinterp constant 2. Now the v in front of this function basically means that it does interpolation on vectors. That's why it's called vinterp2 as opposed to other interpolation functions that are also available in this library file. So let's have a look at how we would use it. First of all, we're going to copy the include line from the documentation, and we're going to go over into our mover CPP where we want to implement this in the body of the tick component. But the include we do not include within the body of the tick component. We have to do the includes all at the top of the file. So that's where I'm going to put mine, and I'm going to put mine after the include of mover.h. So we're going to put in an include for math/Unreal Math Utility.h. Now, what we can do is we can actually use the function within our tick component. Let's just get rid of the code that we've already got in tick component, because we were using that to understand how to call functions on other actors. And what we need to do is, if you scroll up, you can see the way to call this is fmath : vinterp constant 2. So we're kind of doing this : operator that looks inside the fmath class, which organizes together all these math utilities. So we're going to do fmath : and here you can see a bunch of autocomplete coming up for different maths functions included in that header file that we've just included into this file. So you can have a look through, see any of the interesting stuff is in here. I can see a bunch of interpolations, circular interpolations, etc. But we wanted the vinterp constant 2. We can hit tab to complete that, and then open some parentheses, and we can see the arguments that we need to be passing in: the current, the target, delta time, and the interp speed. So let's start creating some variables to hold some of these. So first of all, we need an f vector, which is going to be our current location, and we're not going to set that for just yet. Then we're going to have an f vector for the target location, and then we're going to get a float for the speed. And we're going to have to calculate each of these individually to figure out how we can make this movement happen. So the current location is going to be relatively straightforward. We need to get the current location of the owning actor. So how do we do that? Let's replace this semicolon with an equal sign. And we're going to do a get owner, pair of parentheses. Then we're going to do arrow. So we're going to be calling a function on the owning actor. And we're going to do get actor location, and then a pair of parentheses and a semicolon to end it. So that gets us the current location of the owning actor. Now what about our target location? Well, we know that we've got a property called the move offset. So that's going to be involved here. But we do need to add the original location to this move offset. So for that, we need to capture the original location in begin play. So we need a variable to store it in. So let's go over to our mover.h, and it's not going to be an edit anywhere one, so I'm going to put it under our U properties. It's going to be an f vector called original location. We're not going to set it to anything here. Then we're going to go over into our mover CPP into begin play, remove this comment line, and put our own code, which is going to be that the original location is equal to get owner parentheses arrow get actor location, like so. So now that we've got our original location captured in begin play, we can use it in tick. So we go over into tick and we set our target location equal to the original location plus the move offset. So that's our target location. And finally, our speed. Well, this is essentially the distance that we need to move divided by the time which we need to move over. So if we've got a target location and we've got an original location, we need to find the distance between these two, which we can do with an f vector distance. Then we pass in to the parentheses the original location and the target location. So that gives us the distance between these two vectors, and then we are going to divide that through by, what did we have over in mover, called the move time. So that gives us the speed at which we should be moving. And now we can use these as arguments to our v-interp constant 2. So we've got, first of all, we need to give it the current location, and then the target location. Then we're going to tell it the delta time, which is just already a parameter in tick component, so we just need to pass that through. And then we've got the interp speed, so we're just going to pass in the speed, like so. Put a semicolon on the end of that line, and this is essentially the new location. So let's store that into a new variable, f vector, called new location, equal to this. Cool. Now we need to do something with that new location, because it's no good just having calculated it. We do actually need to move the actor to the new location. So that's what we're going to do. We're going to call it on get owner. So we do a get owner, parentheses, arrow, and then we're going to do a set actor location, and we're going to pass in the new location like so, and have a semicolon at the end of the line. So let's go ahead and compile this and see if it works. So if we go over into the dungeon and select the wall that we want to move, you can now see that the mover component has got a move offset, which I'm going to want to do in the Z direction. And I think I'm going to do -600. And then the move time 4 seconds should be just fine. So let's save that and then hit play and see if it moves. So it's not moving, and there's an error in the output log saying that the mobility of the actor has been set to static, which is why it can't move. So if we select the actor again and we look at its mobility settings, you can see, in fact, the mobility settings of the static mesh component. So select the static mesh component, then look at the mobility, you can see it's set to static, which basically means it's not allowed to move. Let's switch that over to movable, because we do want it to move, and then let's go ahead and hit play. Now you can see in the darkness that the wall was going down, which is perfect. I do think we've got a mover somewhere else in our scene, up on this pillar here, that it's also trying to move, so let's not do that. Let's delete the mover component that we added in there just for testing, and it should give us no errors in the output log. If we go ahead and hit play now, we should just have that wall going down to its target location. So let's challenge you to make it move with the boolean that we created, that U property. So you're going to wrap the code in an appropriate if statement and the appropriate code so that it only moves the platform when that boolean is true. And then Then you're going to recompile the code and challenge you to let's delete the mover. You can see, in fact, the mobility settings of the static mesh component. So select static mesh component, then look at the mobility. You can see it's set to static, which basically means it's not allowed to move. Switch that over to movable, because we do want it to move, and then let's go ahead and hit play. Now you can see in the darkness that the wall was going down, which is perfect. I do think we've got a location, and we're going to pass in the new location like so, and have a semicolon. at the end of the line. Basic mesh component, recompile the code and play and eject using F8. Come back. So let's go and be executed within the if statement. And let's go and hit play. That this would only be and then we're going to select our mover components and check should move. And there you go. The wall starts to move. Hello and welcome. In this lecture we're going to be making our very own scene component for the grabber, and we're going to print out its rotation so that we can see that it is indeed attached to the camera and the camera's rotation is affecting its rotation. Let's dive in and see how this works. Now, if you remember from seeing the demo, I would like to have a little statue in one of these cells and to allow us to pick it up and take it over to this alcove for placement. Now, the problem here is that I don't have that statue and I don't have a way of even knowing if I am pointing at it when I'm trying to pick it up. So that is what we're going to aim to try and solve in the next few lectures. Now, the problem here is that I don't have that statue and I don't have a way of even knowing if I am pointing at it when I'm trying to pick it up.
Hello? Can you hear me? So this is like, okay, this is like main entrance. Are you you would come in from here, like the outside area. You come in, that wall would stay here. Look at this. You see this? It'll be too bright, but there's like a puzzle they'll have to do. They get to get all the, see, like it's colored. That would go there. The purple and green one, those are over here. Okay. And here. Okay. And like, yeah, so they would solve this puzzle, and then they would unlock this. And you would walk down. I'm gonna put stuff over there too. And I don't know what I would do here, but some decoration. And then there'd be a gate here too, and then they'd have to do some puzzle or something here, there. And then you unlock this, and this is where you win. It's like the end of the game. That's the level. Is that cool? I make some a bit more. I can fix that. Look at this effect. It's cool, right? I thought this was really cool. I didn't know how I even. Yeah, basically here they would come. They have to like find these. This one you have to put here, and then this would start to glow. And then these two are over here, right? But to get it, there's like I'll have like a puzzle in here to open this thing. Like the gate that was here. This gate. Right, like this would happen after. And even this, so like when they put this and this over there, then this thing will open and then they can go in and find the secret treasure. Yep. Simple-ish. Close that for a second. Not get. Look, I figured out get. Kinda. What do I even do? Oh. Oh.
So that is what we're going to aim to try and solve in the next few lectures. So first of all, let's put a statue in place for us to use. So I'm going to open the cell door a little bit. So let's click on one of these cells. I'm going to go down to the door and I'm just going to rotate it nicely open so that we can get in. The next thing I'm going to do is it's very dark in here. So I'm going to put a new spotlight here. Let's go to the quickly add button, go to lights and find a spotlight, drag that in to our scene and drag it up the wall a little bit so that basically we are alerting the player to the fact that hey, there's something of interest over in this corner that you might want to pay attention to. And we're going to go to the select the medieval dungeon folder and search for statue. And you can see we've got a golden one and we've got a stone one. I'm going to go for actually probably the gargoyle here. And I need to give it some sort of something at the bottom because I know that this mesh has a hole in its bottom. So if we go and turn it upside down, it's going to look awful because it doesn't actually have a back side. So what I'm going to do is I'm going to take this gargoyle and I'm going to turn it, well, I'm going to actually add a mesh underneath it. So we're going to look for some dirt mesh. And you can see I've got a little bit of dirt here that I'm going to just take and slap on to the existing gargoyle statue actor. So it's dirt mound. And you can see it's absolutely huge in comparison, but don't worry, we can fix that with a little bit of scale tools. So this dirt mound, so I'm going to go ahead and scale this locked in the details pane. Perhaps I'll start with 0.1 and see how small that is. And let's actually rotate the entire gargoyle actor so that we can see properly what we're doing. Let's have a look at that dirt mound. The dirt mound needs rotating.
by 180 degrees, and then let's use the scale tool to make it a little bit bigger. I'm just going to finesse these figures a little bit using the details pane now. I'm squashing it right flat with the scale in the Z and finessed it, I think, just enough that it looks like there's a bottom to that. And now we can put this gargoyle rotated 90 degrees again and try and place it somewhere in the corner under this spotlight. So that's the aim, for us to get hold of this mesh. But how are we going to do it? We're going to need a special component in order to do this, and we could use an actor component, but in this case it's actually going to make more sense to use a scene component. Let's see why. Let's go ahead and go to the root of our content folder, clear out the search, and open up our BP player, and let's open up the full blueprint editor. And what we want to do is essentially to have something that tracks around when we're moving our first person camera. So as I play in here, you can see that I am looking all around and my camera is also looking all around. So what I want is something that points in the same direction as my camera. So the logical thing is to attach a component to this camera which would allow it to automatically rotate with that first person camera and always be pointing, always having its forward vector pointing in the forward direction of the camera. So that's what we're going to do, and that is exactly where we need a scene component, a component that can attach to other scene components and has a transform, has a location, rotation, and scale. So the way we're going to do this is we're going to go to the add button in the components, but we could do this another way. We could also go to our content drawer, go click on C++ classes folder and hit add new C++ class. And then what we can do is we can go and scroll down to where you see it says scene component. So we're going to make a new scene component rather than an actor component. And we're going to go ahead and hit next. Now we're going to call this the grabber because it's a component that's going to be eventually responsible for figuring out what to grab and then grabbing hold of it so that when we move, the grabber takes it with us. So we're going to go ahead and create this class, which takes us over to Visual Studio Code with a grabber.h and a grabber.cpp. And you can see that it's created a uGrabber again with this. We're going to go ahead and hit next. Pointing in the forward content drawer says scene component. So we're going to make a new scene component rather than an actor component. And we're going to go ahead and hit next. Now we're going to call this the grabber because it's a component that's going to be eventually responsible for figuring out what to grab and then grabbing hold of it so that when we move, the grabber takes it with us. So we're going to go ahead and create this class, which takes us over to Visual Studio Code with a grabber.h and a grabber.cpp. And you can see that it's created a uGrabber again with this u prefix for components, and it inherits from the uScene component. So that's how we know it is a scene component, again with that inheritance being the is a relationship. If we went over to the mover.h, you could see that the inheritance is actually from uActor component, so that is a uActor component. But otherwise it looks exactly the same. It's got a begin play, it's got a tick component, and that's because actually a scene component is an actor component. It just adds some more functionality on top. So now that it's a scene component, we should be able to go over into our editor, go to our BP player, and from here go to add and look for the grabber. And the grabber, now you see I had my first person camera selected, so it automatically added the grabber as a child component of that first person camera. So I'd like to challenge you to print the grabber rotation. The way we're going to do this is to get the component rotation this time, not the actor's rotation, because the important thing is actually how this particular component is rotated because it's attached to the camera. We're going to convert it to a string using the toCompactString function of the F rotator this time, because we're not using an F vector for rotation. It does actually have a toCompactString function, however. Then we're going to print that out using the UE log. Remember, you put a star before a string for strange reasons. And then we're going to compile it, test it out, and see, does it change the rotation? Does it move with the camera?
pause the video, and have a go. And then we're going to get component rotation, parentheses, and then from this we need to get an F string, which is going to be the rotation string, which we're going to do by doing the my rotation dot to compact string, parentheses. Now we're going to type ulog, and we're going to have the grabber rotation %s, and then we're going to remember the star before our rotation string, like so. Now let's go ahead and compile this, and it looks like that was successful, which is always nice to see. And then we're going to go ahead and hit play and have our output log docked in the layout so that I can see it at all times. You can see the rotation is indeed being printed out, and as I move up you can see my pitch, the P, is changing. As I turn from side to side, the yaw is changing, but at no point is it kind of tilting from side to side, which would be the roll. So that's why in the compact representation, the roll is always set to 0. So you can think of it as roll, pitch, and yaw like in an airplane. So it does look like this is own scene components, how we can attach them to Hello and welcome. In this lecture we're going to be learning about line traces and sphere sweeps, which are going to help us be able to query the world from our code. We're also going to set up a collision channel so that we can have respond to the grabber or not respond to the grabber. Let's dive in and see how this works. So as far as our code is concerned, it's pretty much blind. It cannot tell what I am looking at right now, and it cannot tell whether I am trying to pick up a gargoyle, whether I might be trying to pick up something else entirely else. As far as the code is concerned, it's standing in a pitch black room and it cannot see anything. So how do we solve the problem of figuring out from code what is out there? Well, essentially we need to switch on a high beam flashlight and look in a certain direction to see what there is. Essentially flash a light into a dark scene. So imagine that hidden in our dark scene, we've got these shapes here. What we might do is take a starting point and an ending point and essentially trace a line through from the start to the end and see what that line overlaps with. This is called a line trace. So when you do a line trace, you essentially can get back either a result which is all of the objects that the line intersected with on its path to the end, or you can just get the first object that it hit. And there's some optimizations that mean that if it hits an object, it actually doesn't do the entire trace at all. So this is how we often do things like shooting guns in first-person shooters, or even, like we're doing here, picking up objects. There's an alternative to the line trace, however, because the line trace can mean that we have to be extremely accurate. If we miss an object by a few millimeters, like this sphere, it won't be picked up. So the alternative is a shape trace, and sometimes more specifically known as a sphere trace if that's the shape we're using, or more generally it's actually known in code as a geometry trace. What we do here is we take a sphere starting at our starting point, and as the name would suggest, we trace it, or we sweep it actually. We sweep the sphere through the world to the end point, and if it intersected with anything along the way, then that is something that the trace will hit. So, for example, we will overlap here with this triangle and the sphere because we've expanded the radius of the search space. Now, there's one more additional thing that we can add to our traces to make them ignore certain shapes in the scene, because, for example, we know that we can't grab hold of this wall, and maybe we want to be able to grab something through the bars even though we might be hitting the bars as we do so. Well, the way to do that is using something called a trace channel, and this essentially creates a list of objects that can respond to the trace and others that might want to ignore it entirely. So let's take a little look at how to set up our own trace channel so that we can pick up objects in our scene. Now, the place to go and do this is over in Settings, Project Settings, then go to Engine and Collision, because this is all about object collision. And in here you can see we have got object channels and we have got trace channels. We're looking at particularly the trace. Project Settings, then go to Engine and Collision, because this is all about object collision. And in here you can see we have got object channels and we have got trace channels. We're looking at particularly the trace channel because what we want to do is figure out how we should respond to a certain type of query. If we go back into our scene and click on an object, and if we scroll down to an area called collision, and there's a bunch of settings here about how this object should respond to other objects in terms of colliding with them. So if we go, at the moment it's got a default collision preset. If we have a look here, there's a lot of different collision presets here, but let's go to the custom one so we can see what is actually involved in collision settings. So we've got an object type. We've got the types of query it responds to, which is query. In this case, that's things like line traces and sphere traces and sweeps and so on. And then there's physics, so that's the simulation of physics and whether it bounces off other objects. But further down, you can see there's the collision responses, and this is split into trace responses and object responses. So what it's saying is, here are some of the trace channels that are already built in. There's a visibility trace channel. This is basically all visible objects. And there's a camera trace channel, which is basically whether the camera should be allowed to penetrate through this object or not. But this isn't too important. These are the types of channel that we have, and we can respond to them differently. You can see here that we can have a block option. There's an overlap, which is an intermediate option, and a completely ignore option. So this is what we're interested in. We're interested in adding in a new trace response channel here. So let's go over to our project settings, go to our trace channels, and click Add New Trace Channel. Then
Discovery Houston, trim to ATO. Beautiful, beautiful.
Then we're going to go in here and call it grabber, and we get to choose how by default objects are going to respond to this channel. I want it to ignore this channel by default so that we have to specifically say that an object responds to this trace channel. I'm going to go and click accept, go over back into our dungeon, and you can see that we're not actually showing the new trace response just yet. So what we're going to do is close down the editor, save the scene, and relaunch from the uProject file. So once that's launched up, let's select our gargoyle again and go down to our collision settings. And sure enough, here we've got our new trace response channel grabber, which for the gargoyle, we want it to block, basically meaning that it will block the line of sight, and so it will show up in either our sphere sweep or our line trace. Great stuff. Hopefully now you've got a better understanding of line traces and sweeps. I'll see you in the next lecture. And sure enough, here we've got our new trace response channel grabber, which for the gargoyle, we want it to block, basically meaning that it will block the line of sight, and so it will show up in either our sphere sweep or our line trace. Great stuff. Hopefully now you've got a better understanding of line traces and sweeps. I'll see you in the next lecture. Hello and welcome. In this lecture we're going to be learning about something called the world object, a very important object in Unreal. We're going to see how we can get the current time in our game from this object and print it out to the console by the end of this lecture. So let's dive in and see how this works. So to be able to do line traces or sweeps, we need to understand another concept, another type of object that exists in Unreal Land. And that object is the world. So we've dealt a lot with levels. So if we go to our content drawer, we've dealt with maps as well. So the map and level we've kind of talked about as being synonymous. However, a world is kind of there in the beginning. In the beginning was the U-world, and the U-world is the type, is the class for basically the environment that we're seeing when we play a game. But it's not just necessarily one level. You can load a level, which is called a U level in C++, which is just a collection of the actors that we should bring into the U world. So you can load a level into your U world, but not just necessarily one level. You may load in multiple levels into a single world. And that's because often we have these streaming levels, we have very large levels where we don't want to load everything, every actor into the level in one go for performance reasons. So we split it up into multiple U levels, and that allows us to bring in only parts of the scene as they're required. So if we have a look at the documentation page on UWorld, I think it describes it rather succinctly that the world is the top level object representing a map or a sandbox in which actors and components will exist and be rendered. If you look a little bit further down, it says that the world can be a single persistent level, basically meaning a level that will constantly be there, or with potentially an optional list of streaming levels, or basically levels that can be loaded whenever we want. Now, why is any of this interesting? It's interesting because it allows us to do line tracing. If we search the documentation here for line trace, then you will see that there's a bunch of functionality here, particularly the one that's most interesting to us is the line trace single by channel or the line trace multi by channel, which essentially allow us respectively to get hold of that first object hit or all of the objects hit by a line trace. And you can see that the list of arguments, especially if I look at the line trace single, the list of arguments has the start, it has the end, it has a trace channel for which to do the trace, and it actually gives us a result in the parameter list, which is a little bit strange, and we will be covering that shortly. But anyway, this is the line trace. We also have the ability to do a sweep. So if we search for sweep, you can see there is a sweep multi by channel. There's also a sweep single by channel. And here, as well as the start and end, you also have a collision F collision shape type that you can pass in. Basically, we click on that F collision shape. You can follow through in the documentation in Unreal to read more about it. And you can see that F collision shape basically supports being either a sphere, capsule, box, or a line. So we're going to be using the sphere in our case, like so, and we'll see how to construct these later on. But you can see why we want to get hold of that UWorld, why it's important to us. But the question is, how do we get hold of the UWorld? And once we've got hold of it, how do we use it? Well, let's go and have a look in Visual Studio Code. On every component and every actor, there is a function called getWorld. And if you type getWorld and then parentheses, this returns an object of type UWorld. In fact, a pointer to an object of type UWorld. So let's store that. We've got a UWorld pointer, which is going to be, let's just call it the world, shall we? And that's equal to getWorld. And then we can put a semicolon at the end there. Now, in order to actually get hold of anything from this world, we're going to use the arrow operator. So we're going to do world arrow, and then we would be able to go and have a look at some of the details of that world. But before we do that, we need to include its header file, because otherwise this C++ file, when the compiler gets to it, isn't going to know what is included inside a UWorld type. It has no information about a UWorld whatsoever. So to fix that, we need to look at our documentation for UWorld, scroll to the top, and look for that place where it says include, and that gives us the include we need to use. You can see include quote engine / world. That's what we need. So we'll just put that after our grabber.h here. And now, if we hit control space, we should get a list of the things that we can do. And now, you can see include, we can find our line trace, we can find our sweep by multi or single. So I'd like to challenge you to print the time elapsed. This is a property available on the UWorld object. You're going to find the time seconds property, read up about it in the documentation, which is linked against this lecture, and store it in a variable of the appropriate type. Again, looking at the documentation will tell you what the type should be. And then log that to the console, again using the appropriate format specifier. Pause the video and have a go. Okay, welcome back. So we're going to make use of this if I search through for time in the UWorld documentation, you can see there is a float called time seconds. That's the one that I want. In this case, this is the game time. So if you slow down or speed up time, this gets slowed down or sped up as well. But there are ones where that doesn't get affected. There's different ones. You've got the time seconds, the unpaused time seconds. There's also the real time seconds, which doesn't get paused or changed in any way. So I'm interested in the time seconds. It doesn't really matter which one we use because they're all floats anyway. So I'm going to create a float called time and store the world arrow time seconds in there. Now, for short, we don't actually need to put the world into its own variable. It's quite short enough to just call getWorld. So that's what we typically do. We'll do getWorld, then arrow time seconds, like so. Now we can do a log, which we're going to say the current time is, and then we're going to do a %f because we are printing out a floating point number here, and then we can give it the time as the input into the log. Now let's go Control Alt F11 to live code, and then we're going to open up and dock the output log and hit play. And there you can see that we've got a current time which is counting up in seconds as the time elapses in our game, like so. And if we actually hit the pause button, you notice that the time stops going, and if we hit play, it just resumes from where we were. If you wanted to, you could experiment with using the real-time seconds and see whether that effect happens, but I'm not going to here. We've shown that we can get hold of this UWorld object, this world object that we are currently in, and that we can get properties from it using our arrow operator. Pat yourself on the back, and I'll see you in the next lecture. Hello and welcome. In this lecture we are going to be drawing debug lines into our scene so that we can visualize what it is that a line trace is doing, or what it should be doing, and figure out if our values that we're calculating are correct. Let's dive in and have a look. So as we can see, our sweep multi-by-channel function requires a start and an end vector. Now, it can be a little bit hard to figure out what's going on with these functions when we actually use them, because if you start using it and you don't get back the results you're expecting, you can sometimes leave yourself wondering, well, did I ask the right question in the first place? Did I send in the right start and end vectors even? Well, to figure that out, what we're going to do is use another function here called the draw debug line, so that we can definitely see where the start and end vectors are, basically by drawing a line between them. And given this is exactly the kind of thing that's going to be done by our sweep, then this is a good way of seeing, first of all, whether we've got the right inputs in the first place. So you can see here that the draw debug line requires quite a few arguments, but not all of them are actually required. Only the first 3, 4, or 5. So we've got the first thing that comes in is a U world, where we know how to get hold of the world now. We've got then the line start, which is a vector. We've got a line end again, which is a vector. Then an F color, which is something we haven't come across before, but you can click on it to find out what it is. And essentially it is a type like F vector that represents colors. And there are a few handy colors already built in for us that allow us to just say, hey, we want black, we want blue, green, whatever. You can just use a color name rather than having to specify the RGB values. And then the final few through here are whether we've got the persistent lines, which tells us whether the line sticks around or whether it goes away at the end of the frame, tells us the lifetime, so how many seconds does it stick around for, the depth priority, and the thickness, neither of which we will be using. So the other useful piece of information on this documentation page is the include. So you can see here, to use this function, we need to be using the header file that declares it, which is the hash include draw debug helpers. So let's go ahead and get that first of all, because that's going to make sure that autocomplete works in Visual Studio. If you don't have the header files, then Visual Studio doesn't actually know how to autocomplete these functions. Then we're going to go down into tick component, and I'm going to get rid of our log message for the get world, get time. We'll get rid of all of this time, in fact, and you know what? We're just going to empty out our tick function. Everything after our super : tick component we're going to remove, and we're going to start with the draw debug line. So draw debug line, and then open some parentheses. If you hit a control space, then you can see the parameters we were just talking about, and some more information that wasn't available there, such as their default values. Some of them have default values, particularly after persistent lines. You can see the default value is false, so you don't actually have to provide an argument if it has a default value. But you can see that the color doesn't have a default value, so we do need to provide everything up to that point. So the first thing is the world. Little mini challenge. How do you get hold of and pass in the world into draw debug line? You do a get world parentheses, like so. Then we're going to need a start and an end. So for that, I'm going to create two variables just before draw debug line, and I'm not going to fill them out just yet. So f vector start and f vector end, and those are going to be our next two parameters, start and end. And then we need to give a color. To do the color, we can do f color : and then we can use one of those predefined colors, such as red. Is always a good one, you can easily see it. And then in this case, because we're doing it in tick, and we're doing it every frame, we're writing this line to the screen, we can just use the persistent lines equals false. So every tick it will be redrawing this debug line, close the parentheses, and then we can put the semicolon at the end of the line. So what are these start and end values going to look like? Well, at the start, it's literally just going to be the location of our grabber component, because that's going to be attached to the camera. That is a good start location. Now remember that there is a forward vector for this component, for the camera, for the grabber, and that forward direction is going to be pointing out from the camera, out into the scene, always pointing forward. So what we want to do is take our start vector add the forward vector multiplied by some amount. Basically, that some amount is going to be the maximum distance that we are going to look for the object. So you might have 1 or 2 or 3 meters as the amount, and then we're going to end up with an end vector. So the start plus the forward vector of the grabber is going to equal the end vector. So that maximum depth that we want to look into the scene is something that we might want to configure. So we'll put it as a U property on the grabber.h. Let's go over to the grabber.h and create a private section, make a U property that we're going to make edit anywhere. And then we're going to have the type be of float so that it can be any numerical distance. And we're going to call this the max grab distance. And we'll set it to a distance of 4 meters by default. Maybe that'll have to be 400 because the default unit is centimeters. So I'd like to challenge you to calculate those starts and ends. Use the get component location in the first instance. Use the get forward vector to calculate end, and multiply by the max grab distance that we have just figured there. Then compile, play, and eject from your actor, because this line is going to be going straight down the camera. You may not see it initially. So eject, come and this is simply just going to be the get component location, and then the end rather, is going to be the start plus the get forward vector multiplied by the max grab distance, like so. Put a semicolon on the end of that line. We're going to go ahead and compile, and if it compiled successfully, let's go ahead and hit play. Then get our mouse in the viewport, hit F8 to eject out, and if we we step out of ourselves, you can see the line clear as day coming from where our camera was all the way down into the floor, and probably if I come out, we may even be able to see that it's poking a little bit out of the bottom of the floor as well. That's 4 meters for you. So we've got a start, we've got an end, and if we were to use this line, this would be an excellent one for the input parameters to our geometry sweep that we're going to. Hello and welcome. In this lecture we are going to be learning about references, an alternative to pointers, and we're going to see why they're different, why we might want to use them. Let's dive in and see. So as well as pointers, there's a very similar related concept called a reference. Now, both pointers and references are essentially just a memory address. They both store a reference to where another variable can be found, and in this way they are incredibly similar. The difference between the two comes to basically down to whether they can be reassigned. Basically, can they point to a different address after they've first been created? In the case of a pointer, that answer is yes. You can change a pointer to point to a new memory address, a new actor, a new component, whenever you like, as long as it has the right type. A reference, on the other hand, can only be set up once when you first create it to point to another variable. It can't then be changed again. And this is a safety feature because repointing variables can lead to problems where those variables might disappear, or where you set that pointer to null. A null pointer is essentially a pointer that points to nothing. And trying to do stuff with a pointer that sets to nothing can actually crash your engine, which isn't an ideal result. With references, because you have to give them a value when you first create them, they can't be null, so you cannot get these null pointer crashes. So let's start to have a look at some of the syntax involved. So when you access content with a pointer, you have to use some special syntax. You have to put this star in front of the pointer to make sure you're getting the value in the pointer, not the memory address. With references, because you never really need to get hold of the memory address, you can just use the variable as if it was the variable it's pointing to. You don't have to use any special syntax. Now there's accessing the address. So with pointers, you get hold of the address automatically when you use the variable. With a reference, you have to use special syntax to do that. You have to use the address of operator, and it will get you basically the same address as the original variable. And then there's changing the address. With a pointer, we've seen that you can assign the address and use the address of operator to do that. With references, this isn't allowed, so there's no syntax for it. And finally, what if we want to... to change the value that we're pointing to, not the address, but the actual value being stored at that address. Well, with pointers, you got to again use some special syntax. You have to put that star and then assign something. So the actor pointer you assign to the star actor pointer. With references, again, because you can't change the actual address, you don't need any extra syntax. We can drop the extra syntax and just have the actor reference equals actor, means that you are overwriting the value in the pointed to location. So that's all a bit theoretical. Let's have an actual example. So if we had a float that was perhaps storing the damage done to us in the game, and in that we are storing the current damage is set to 0. No one's done any damage to us. Now we might want to create a reference to this to, instead of copying it around, we might want to pass it into a function but without actually changing it. The way we can do this is to have a float and then put the ampersand after the float, and the ampersand says that this is a reference to a float. It is not a new float itself. It doesn't allocate any float memory, it just allocates pointer memory. And so we can call this the damage ref, and we can set it equal to damage. We don't have to take the address of or do anything like that. It automatically knows, well, this is a reference and this is a variable, so what you're trying to do here is set up a reference to that variable. And sure enough, if we go and ulog, then we can print this as if it were just a regular float. So we can say damage colon and then %f, and then here we can do just print damage ref. We don't need any special syntax. We can use it just like a regular variable. Let's go ahead and hit play after compiling, have a look at that output log, and sure enough the damage is coming out at 0, which was the value that we set. But that doesn't necessarily prove that I haven't made a copy of that original variable. So I'd like to challenge you to try changing the value and see what happens. So use the reference to damage, to set a new value, and then print out the original value too. So the original value next to the reference value, and have a look. Are they the same or are they different? You only change the reference, but does it change the original as well? Because that would imply that they are both the same variable. Pause the video and have a go. Okay, welcome back. So let's give this a stab. So to change the reference now, we're going to do damage ref equals, and this time we're going to say that we did 5 damage. And notice I haven't had to use any special syntax here. It's not repointing the reference because we've already declared it and set its reference up on that first line when it's created. We can't do it again, so now we can just be setting the value. So what I can do now is we've got the damage ref is in the log. Let's also put a damage and %f onto that same string, and then pass the damage in here as well. And then we're going to compile and have a look. Let's hit play, go into our output log, And sure enough, it's printing out damage ref and damage as both having the new value that we've set, the value of 5. So in essence, what we've got here is two variables that point to the same piece of memory. You could almost say that they are the same variable but with different names. So this has the benefit of not needing a copy, just like a pointer, but it also has a lot more benefits because it's so much easier to use. We don't need all that extra syntax, and it's also safer to use. So as long as we don't need to repoint anything, using references is generally preferable. Now let's do a quick review of some of the symbols we use here, because they can get a little bit confusing. They're used a lot in C++. So the ampersand and the star symbols, let's have a look at them in context and what they mean. So when we are using them, in an expression, here are some code examples. You might see the star before a variable, you might see the ampersand before a variable. What does this mean? Well, with the star symbol, the syntax of putting it before the variable means we're getting the contents at actor pointer. Now, with the ampersand, if you put the ampersand in front of a variable or in front of a reference to a variable, it's saying that it's getting the address of that variable. It's getting the address of the actor or the address pointed to by the reference. Now, when we are declaring, when we're using it in the type of a variable, the stars and the ampersands have almost the opposite meanings. So the star means that this is a pointer to a U actor, and the ampersand means this is a reference to a U actor. So just remember this, that there is a completely different set of meanings whether you're using them with a variable in an expression or whether you're using them in the type declaring a variable. Now, I won't go into it in too much detail, but to add insult to injury, these can actually have other meanings in other contexts. That ampersand can mean a bitwise and. The star, as we've already seen, can be used with strings in the ulog. So this isn't necessarily all of the meanings of these two symbols, but they are pretty much all the important meanings referring to pointers and references. Great stuff. So we've learned about pointers, references, how they relate to each other, how they are different. Hello and welcome. In this lecture, we're going to be learning about a strange phenomenon called an out parameter. This is a parameter that instead of passing the value in C++, we tend to pass the value out of a function. And we're also going to see about something called a constant reference and how these two concepts are kind of intertwined with one another. Let's dive in and figure this out. Now, the real place that references shine is in parameters to functions, because every time we create a float delta time like this in our tick component, what we're doing is we are taking a copy of that original float and we are passing it in to the function. So instead of doing that, what we might want to do is take a reference to it and pass that in instead. So let's imagine that we were to create a function in grabber.h called print damage, and as a argument to this function we want to pass in a float damage. Now this, as I said, is going to make a copy of whatever we pass in and copy it into that variable created, this parameter variable, inside the print damage function. And we do need to have a return value of void here as well to complete it, and a semicolon at the end. Let's go over into the C++ and continue this conversation. Let's create the print damage in here. Let's put the uGrabber class in front of it, and let's put some braces instead of the semicolon. So we've got a copy into the damage parameter variable, and it's safe because if I were to do damage equals 5, I'm only changing this variable here within print damage. I've got a copy of it, it's my own, I can't mess it up by accident. Now, what if I didn't want to make a copy? My alternative would be to take a reference. So what I can do here is I can put a float reference going into print damage, and I need to update that over in the C++ file as well. And then I might have this log message that we're using the reference for. Let's go and take this down and put that into print damage. So now we take our damage and we're printing it out. Let's update the log statement to say damage is this. Okay, so damage is this damage. And in our tick component, what we can do is we can do print damage and pass in our damage variable and put a semicolon at the end, and we can get rid of our damage reference for now, because what we've got going on now is a damage float. It's created in tick. The memory for this has been created here in tick, and then we go and give it to this print damage function. But because the parameter is a reference, we aren't actually copying this damage. We are taking its address and storing that in the reference instead, so that when we use this reference down the line, we're actually accessing the original piece of memory. So no copy has had to happen for this to print the damage. Now let's just check that this is doing what we would expect it to do. If I change the damage, the log indeed image should be equal to 2, like so. And if I wasn't careful, if I thought I had my own copy, I might think that's okay. But actually, in the tick component, what we've done is we've changed the original variable. So if I put a ulog in here to inspect that original damage variable, and we put %f and pass in the damage here, let's live coding compile that, and we're going to hit play, have a look at our output log, and you can see that now the damage and the original damage have both been modified. They've both been changed to the number 2, which isn't great. You know, you could accidentally do a lot of damage, if you'll excuse the pun, by changing the variables that you weren't expecting to change. And here comes another use of that const keyword that we've seen in the past. If I stick const in front of my float reference, then what I'm saying here is that this should be a reference that you cannot change. You cannot call any non-const functions on it, you can't set it, you can't in any way change the contents of this variable. You can only use it, you can only read it, you can only see what is in there. So if we go back into our grabber CPP, we need to make sure that we put const here in the parameters as well, and we can go ahead and compile, and you see we get a build failure, and the error is saying that damage cannot be assigned to because it's a const variable. So that gives us the protection we need. So generally speaking, if we are trying to pass a variable in an efficient way where we don't want to take a copy, then we will always use the const keyword as well as using a reference, because this prevents us from accidentally changing that contents. Now, however, sometimes you do want to use it to change that value, and what we might have as an example, we might have a Boolean return value, and we might want to say has damage, but we might also, as we've done in Blueprint in the past, want to have a second return value. So we might say, have we got any damage? And what is that damage? Well, in this case, it actually makes sense to use a simple non-const reference, a float reference to the damage. And typically we would actually call this out damage, just to make it really visible that this is what's known as an out parameter. It's not a parameter for passing things in, it's a parameter for passing things out. Now, it can be a little bit of a weird quirk of C++, and it can be hard to spot. But generally speaking, if you see any parameters that are a reference but aren't marked as const, then you can pretty much assume that somebody intended to use that as an out parameter. So that's what we've got here. We've got has damage, and if we were to go and implement this over in the CPP, then we can put the uGrabber class in front here, and we can put braces, parentheses here. We're going to comment out the line in print damage what it's not happy about, because we're trying to set a const reference, and out damage, just to make it really visible using a reference, because this prevents us from accidentally changing that contents. Now, however, sometimes you do want to use it to change that value, and what we might have as an example, we might have a Boolean return value, and we might want to say has damage, but we might also, as we've done in Blueprint in the past, want to have a second return value. So we might say, have we got any damage? And what is that damage? Well, in this case, it actually makes sense to use a simple non-const reference, a float reference to the damage. And typically we would actually call this out damage, just to make it really visible that this is what's known as an out parameter. It's not a parameter for passing things in, it's a parameter for passing things out. Now, it can be a little bit of a weird quirk of C++, and it can be hard to spot. But generally speaking, if you see any parameters that are a reference but aren't marked as const, then you can pretty much assume that somebody intended to use that as an out parameter. So that's what we've got here. We've got has damage, and if we were to go and implement this over in the CPP, then we can put the uGrabber class in front here, and we can put braces, parentheses here. We're going to comment out the line in print damage what it's not happy about, because we're trying to set a const reference. And essentially what we could do in here is we could do some code, we could see if we've got some damage, and then we would print out, yes, okay, out damage equals 5, so that's the damage that's been done. And we're going to return true, because we've got some damage that's been done. And this we can now use in somewhere like tick component to get hold of the damage. So here, instead of setting the damage 5, we might get the damage and print it if there is some damage. So we can say something along these lines. If has damage, and then we pass in the variable that we want to be populated with the damage, so damage, for example, and then we can have the body of our if statement, and we could only call print damage, for example, if there is any damage to be displayed. And we can remove this ulog entirely. So this is the way that we use non-const references as out parameters, a way of getting multiple return values out of a function. And typically when we do this, when we are calling to this function, we will create the variable, but we won't give it an initial value. So on line 39, basically I've got a float damage defined. I pass it in straight away in the next line. And this is another telltale sign that you are using an out parameter. I haven't given it any value. Right before I've passed it into a function means that I'm expecting that function to put the value in for me. So this can be hard to spot at first, and it can be a little bit confusing, but these are the two rules that I would like you to remember. If you see a variable declared and not given a value and instantly passed into a function, ask yourself whether that's an out parameter. And the other rule is if you see a reference as a parameter, but it isn't const, then that might also be a hint that this is an out parameter. And of course, if the Hello and welcome. In this lecture we're going to be setting up our first geometry trace so that when we go and look at our gargoyle and we get close enough within range, then sure enough it prints out the name of the actor that has been hit by the trace. Let's dive in and see how we can do this. So we're finally ready to tackle this sweep single by channel. There was a lot of pieces that we had to have in place to make it work, but finally we're here. So let's have a look at the syntax of this function. So we are in a much better place to understand what was going on here when in these types. So the return value is a Boolean, which basically tells us whether or not we found anything with the sweep. Now, the second argument, as you can see here, it's a reference. It's got this ampersand, and it doesn't matter whether there's a space after the ampersand or a space between the variable name. It's all the same as long as there's an ampersand after the type. saying that that type is a reference. And it's a type called an f-hit result. You can see that it's a struct. So this f-hit result is the out hit. That is the result that comes out of the sweep. We can see what things have been hit, and it's a struct because there's multiple different things, pieces of information that can come out of this sweep. Then we have a const f vector reference. So this is taking our start vector by reference instead of copying it. Same with the end vector. Then we've got a rotation. So this is the rotation of the shape using an f-quat, which is an alternative struct to using the f-rotator. We'll see how we can basically just put in a 0 rotation here because we're using a sphere. It doesn't really matter. The next thing that comes in is the trace channel, and we'll see how to figure out what our trace channel is called in C++. And then we've got our collision shape, which will be the last argument. We'd move these functions we've been using as examples for const references and out parameters, and we're going to create a new U property, which is going to be edit anywhere, and it's going to be a float called the grab radius, and we're going to set that to 1 meter. So let's go over into the C++ now and remove the references to print damage and has damage, and we can remove any of that from the tick component as well, the whole if statement and where we're passing in the damage. Because here we're drawing our debug line, and now we want to make a call to our sweep single by channel. So we're going to type sweep. So we're going to type call. So let's go over into the C++, the tick component as well, the whole if statement parentheses, because we know that this is a function on the uWorld object. Then we're going to do an arrow because we know that getWorld returns a pointer. And then we're going to do a sweep single by channel, like so. And we're going to have to input an out parameter for it to populate as the first argument here. So we're going to create a variable that's going to be empty that will be populated, and it's got to have the right type. So it's going to be an if f hit result, and we're just going to call the variable itself hit result. Put a semicolon at the end because we're not initializing it, we're not giving it any value, but we're going to pass it in for it to be given a value by the sweep single by channel function. So that's our hit result. Then we need to pass in the start and end vectors, which we know are going to be not copied but taken a reference to. Now we need to populate the rotation, which we can do with a simple f-quat : identity, which tells basically that this is a no rotation. That's just a bit of a weird language for it. It's a mathematical speak for meaning that this is no rotation. Next up, we need the trace collision channel. Now, how do we go about finding finding that trace collision channel? Well, if we go over to the folder that holds our project and we go into config, and then we're going to go to the default engine ini, right click that and go open with Visual Studio Code. And in here I'd like to search for grabber. So you'll be able to see the collision response channel for the grabber, and it's basically been set up here in the default engine ini. It's only mentioned once in the whole file. And you can see the channel name. This is the channel name in C++. It's not very obvious, but it's ECC Game Trace Channel. So we can go ahead and copy that, and then we can go back to our grabber CPP and paste it in here as the trace channel that we want. Now this line's getting rather long, and what we can do to compensate for that is we can actually put each of these parameters on separate lines, or at least spread them out. So maybe the start and end are on the same, the identity quaternion is on one line, the trace channel is on another line, like so. And that just gives us a little bit more space for reading these long argument lists. Now if we head back to the documentation, we can see that the next thing we need to pass in here is an F collision shape. So we need to construct a shape. Maybe we'll do this as a separate variable up at the top. I'll just do it before the F hit result to make it super clear that the F hit result is actually an out parameter. I'm always going to leave that as the last thing before the call to the function. So we're going to create an F collision shape, which we're going to call the sphere, and we're going to set it equal to F collision shape : make sphere. So this is going to create us a new sphere collision shape, and the argument to this function is the sphere radius, which we have got as the grab radius variable that we've configured as a U property. Put a semicolon on the end of this line, and we can pass in the sphere as our final argument to the sweep channel function, and put a semicolon at the end of that line. Now, one more thing is that this function we know returns a boolean, which is whether we've hit anything. So I'm going to put the result into a boolean variable called hasHit, and that's what we're going to be using later on in this function. So I'd like to challenge you to print the hit actor's name. So now we've got this sweep happening, we should be able to get the result into a boolean variable called hasHit. I'd like to challenge you to on in this function. So I'd like to use an if statement to print print if we have anything at all. So if that boolean is true, that's when we're going to print out the actor name. You're going to get the actor that the sphere trace has hit by using the hit result struct. It's got a method on it which you can access with the dot operator because it's a struct and it's not a pointer to the struct. You can do a dot get actor and use the parentheses, and that returns you an actor pointer. And using the actor pointer, you can get the actor's name using the get actor name or label method. And think about whether you want to use the dot or arrow operator for this. And then compile and test having printed out that actor name and see what you can hit in the scene. Pause the video and have a go. Okay, welcome back. So we're going to start off with creating that if statement. So if has hit, then we're going to put some braces, and we're going to do, first of all, we want to get hold of that actor pointer. So a actor star hit actor is equal to the hit result dot get actor parentheses, like so. Then we're going to do a ulog, and we're going to write hit actor colon %s, and we can do hit actor, and because it's a pointer here, we can do hit actor arrow get actor name or label, then some parentheses, and because this is a string, we have to put a star at the front of the whole shebang so that it can properly display it in our UE. Log. Okay, so we now need to just go ahead and compile this. Then once we're in the scene, let's open up the output log, and you can see the thing. So what I'm going to do is I'm going to put in an else to our if statement here, put some more brackets, and I'm going to do another ulog. And this time the text is going to say no actor hit. Let's recompile and go and play in the editor, and you can see it now. It's saying no actor hit all the time until I go and start looking at the gargoyle, and now it's saying that the gargoyle's the thing being hit. If I move too far back out of our 4-meter range, you can see that it's saying no actor being hit again. Great stuff. So we have now done a geometry sweep with a spherical object, and we can see that it is indeed reacting only to the actors in our particular trace channels, such as the gargoyle is the only one that we set up at the moment, so that's the only one that it's finding. I'll see you in the next lecture.